Design point I have found for Vasimir has a thrust-to-weight ratio bounded above by 2 10 to the minus 3. Folks, if you walked into a used car dealer and he told you, I have a car for you that has 1,000,000 miles per gallon, but it will take you a week to get out of the parking lot, would you buy that car? I rest my case.
This is not the point.
I think,
You're finished?
Yeah.
your turn.
Yeah. Back down. I'm sorry.
Okay, after this presentation, rather technical, I perhaps will rather give you the point of view as a leader of the French chapter of the Mars Society, that is the point of view on the communication, on the image of this device and of its impact on the agencies and on the public. In fact, as a propulsion engineer, I was very attracted by the physics of this concept, which are very good, and I had the chance to visit Changdia's laboratory in 2001 and was really impressed by the seriousness of the job, the work that was performed there. But in fact, by visiting this lab, I saw only one part of the problem, and this is the important point in this affair. What I saw and what Franklin Chandias is working on is the engine itself, and what has been shown by Robert just now. But the problem of this engine is that if you want it to be really efficient, that is to have it functioning at very high ISP, you need a very powerful power generator. You need much electricity, and in fact, the efficiency is directly related to the power you are able to deliver to this engine. And this is a problem because to deliver this energy, you need, in fact, a nuclear generator. Solar power is not a possibility because if you look at, for instance, at the ISS, the power is about 100 kilowatt. And here, if we look at possibility to apply the Vasimir concept for Mars spacecraft, or say 50 tons or something, or 100 tons, it is not 100 kilowatt unit, it's rather 100 megawatt, a factor of 1,000. So imagine an array of solar panel 1,000 bigger than the space station. It's not applicable. So you need nuclear electric generator. The technology, we know it. We can surely do that. But the problem is that the specific power of such a generator is awfully great. What we need, what we call specific power, is the mass per kilowatt, in kilogram per kilowatt delivered. And what we are able to do with today's technology is about 50 to 30 kilogram of mass per kilowatt delivered for the whole generator. That is the reactor, the nuclear reactor, the shield, the turbo alternator, and most of all, the radiator, because the problem of generating electricity with a nuclear reactor in space is that you have not cold source, cold dump on the Earth. You use a river or the sea as a cold source of the machine. But in the space, you have to expel excess heat through radiators, which are very huge and very massive. So if you have, for instance, even, be optimistic, 10 kilo per kilowatt for a generator, if you want 200 megawatt, imagine that about 2,000 tons of the generator. So there is really a problem. And the point is that this problem is not raised to the connaissance of the public, of the agency. As it is presented today, it is presented as a solution to get to Mars in 40 days. And that's simply a lie. This is not possible with today's technology. And saying that is very bad, because it is a means for the space agency to defer the decision to go to Mars, because they say, let us develop this wonderful engine and we can be on Mars in 40 days only. So they are excused to defer the decision to go to Mars. And to the public, it is a rather different situation, because on one end, it makes the image of the travel to Mars more sexy, more affordable. It said to have 6 months travel, you have only 40 days. It's good. So it's a positive side of this affair. I think it is always very bad to lie to the people. Remember the ISS situation. At the beginning, it was sold as a fantastic shop where miraculous materials or miraculous medicines would be produced, and in the end, we see nothing. So the public is very conscious of that, and the general impression is that the science and space people have lied to them and sold something which is funny thing. And my opinion is that we should be very careful not to do that again. And so, yes, the Vasimir concept is an interesting concept, and probably it's wise to put resources to develop the research on this topic, but on two conditions. First, that in parallel we put money to develop a nuclear electric generator light enough to be able to serve such an engine, and the second one is that we tell the truth to the public.
Next is Jeff Landis.
No, I'm sorry. Preview didn't hide.
It's okay. You should just be able to double click that.
Yes. No. Let's pretend.
Is there any reason to have to just double click this one?
I didn't have that
Looks
one
like we have a
going.
hand.
This preview has got itself hung up. Oh, here you are. Okay. Now can you control PowerPoint? Okay, you're good to go.
Well, good morning. I'm Jeff Landis. I'm with the NASA Glenn Research Center, which in fact for many years had been the NASA center that works on advanced propulsion. Actually, I should apologize for the slide. I grabbed some slides from an old lecture that I did on advanced propulsion for space at MIT, just because they had some good pictures, and I wanted to show some very good pictures while I was talking. I think maybe we should back up a little bit and talk about what is Vasimir and why Vasimir might be a good thing and why it might be a bad thing. Vasimir, in fact, is an acronym that stands for Variable Specific Impulse Magnetoplasma Rocket. But Vasimir is just one of many different concepts for how you might do electric propulsion in space. And I'm showing you, electric propulsion is real. We do this in space. There's real hardware. It has flown in space. In fact, back in the late 1940s and early 1950s, Werner von Braun told his chief engineer, Ernst Stuhlinger, well, you should make a rocket engine that works on electricity, because this could be very efficient. We can get more efficiency than a chemical engine. And Stuhlinger later told the world, well, I thought that this was a crazy idea, but it turned out, I was thinking about it, and every other idea that Werner von Braun had turned out to be a pretty good one. So I said, well, I'll go through and work on this idea, even though I don't think it's a good idea. So he worked on it. He demonstrated an early electric engine, an ion engine. He then said, well, okay, we have a proof of concept. It's very inefficient. And he gave it to the NASA Lewis Research Center, now called the NASA Glenn Research Center, and said, okay, you guys figure out how to make this practical. And a guy named Kaufman went on to develop the Kaufman ion thruster, which was the first ion engines. These first ion engines were tested in a test called Solar Electric Rocket Test in 1964. And it tried actually it had two different ion engines on it. And actually only one of them worked. They had 50% efficiency on the function. One of them worked, one of them didn't. But the one of them worked showed that yes, the concept does work. We can get thrust in space. The particularly question that they needed a space test to answer was, would the neutralizer on this engine work? So the ion engine, in fact, works by pushing, I want this to go to the next slide. There it goes. The ion engine works by ionizing a gas. In fact, they started with mercury. And then once you have these ions, you can accelerate the ion across an electric field that pushes the mercury out the back. What's a rocket? A rocket's something that you push mass out this way, makes you fly out that direction. Well, the tricky part with the ion engine is these are ions going out, so it's charging up the spacecraft. Every ion you push out this way adds some electric charge to the spacecraft. So part of the ion engine development was a neutralizer that shoots electrons out at the same rate. They needed to make sure that this worked. It did, in fact, work fine, and ion engines have been working in space. After the 1964 test, they were tested again in 1970, and then there was a huge gap. They developed these ion engines, they worked, but nobody actually wanted to fly them on a mission. Everybody said, well, they'd be very efficient, but somebody else ought to fly it first. I don't want to be the first one. So, in fact, the Deep Space One mission in 1998 was the first mission to actually use ion engines for a demonstration mission. It flew by a comet, Comet Borrelli, I believe, and also by a little asteroid, asteroid Braille, just to demonstrate that ion propulsion does work. In fact, since then, we have the next ion engine. I think I just showed a picture of this. We've been testing this in our vacuum chamber at NASA Glenn. It has now been running for 30,000 hours continuously, 3.5 years. When the Deep Space One went in space, I think it had thrusted for as long as all of the other engines in space had been used. Well, you might ask the question, okay, well, this is great, but why? Why use any sort of electric propulsion? What's wrong with chemical rockets? Well, this is a parameter. The previous speakers mentioned something called ISP. How many of you know what ISP is? Let's see how many rocket scientists are here. Okay, about 2/3 of you know what ISP is. Okay, very good. For the 1/3 of you who don't know, ISP stands for specific impulse. It's a capital I for impulse, little sp, specific. What this means is how much thrust you get per unit mass flow of propellant. And the mass flow of propellant is actually measured in weight units, so it oddly comes out in units of seconds. This is actually equivalent to the exhaust velocity, because the faster you throw your propellant out, the more momentum you get out of a unit of propellant.